Hello everyone, welcome back to Nunley Math. Thank you so much for joining us here today as we talk about graphing linear equations in slope-intercept form. This is, I believe, the fourth, maybe the fifth video in our linear equations and linear functions unit. So far we have talked about how we can generate linear equations to model different patterns that might occur either as word phrases, as pictorial representations, and in our most recent video we talked about how they can be used to represent arithmetic sequence patterns. And we've taken those linear equations and we've talked about the fact that a pattern is considered to be linear if it has some kind of a starting point and then a constant rate of change. Or we start with a particular value or a particular number and we are always adding the same amount over and over. We're adding repeatedly. And then we talked about the fact that you can write your linear equation in a form where y equals mx plus b, and m is that constant rate of change, and b is the starting value. Or sometimes we refer to it as the slope and the y-intercept. And we're going to look at that a little more closely today. So let's do this. I'm going to give you a linear equation, y equals 3x minus 8. And I want you to notice a couple things before I graph this. Number one, based on our pattern, y equals mx, we're going to be growing at a constant rate of 3. So whatever this pattern happens to be, it's growing by 3 every time. And when we have repeated addition, or repeatedly adding 3, repeated addition is the same as multiplication. The only thing we're not sure about is how many 3's we're going to do. That's what the x is. So we've got a certain number of 3's, and then we also know that we're going to be starting at -8. In other words, in position 0, we have no 3's take away 8, or we have -8. If I plug a 0 in for x, 3 times 0 minus 8 gives me -8. So this does meet the condition of being a linear equation or a linear function because it does have a constant rate of change, 3, and it does have a starting point of -8. I want to show you what this looks like as a graph. If I start off with x being 0 and I have my -8 as my result, that can be shown on a coordinate plane by going to the right or left 0 spaces and going down to -8. Hopefully graphing on a coordinate plane is nothing new to you. Just remember that right and left is our x coordinate. I guess I could write that in for you since I didn't bother to type it. Here we go. Right and left is x, up and down is y. So anyways, so when I graph that, I go over 0, down 8, and this point represents that combination. When we look in position 0 of our pattern, we're going to get -8. And then I want us to think about my rate of change. The rate of change says that every time x gets bigger by 1, I'm going to be adding another 3. So in position 1, I'm going to have my -8 and 1, 3, which would be a -5. But I can represent that graphically this way. I'm growing 3 every time x gets bigger by 1. So I come over here to my first dot, this 0, -8, and I say, let's go up 3 spaces. Notice 1, 2, 3, every time I go over 1. That's going to give me the second value in this pattern. Whatever's in position 1, if I put a 1 in for x, 3 times 1 minus 8 is -5. And I can use this rate of growth, this constant rate of change, to tell me how quickly my graph should go up, because it should always go up 3 every time x goes up 1. Up 3 over 1. Up 3 over 1, up 3 over 1, up 3 over 1. In fact, every value that falls along that line is a possible combination for this equation. So if I want to know what happens when I put a 2.5 in for x, 3 times 2.5 is 7.5 minus 8 is -0.5. If I go over 2.5, I end up here at -0.5. Everything on this line is a solution or a possible combination of x's and y's that make it true. Now, hopefully there's something very obvious here that you have already noticed, and that is that our graph forms a line. A line. That's the reason we call this a linear equation or function, because every pattern that fits this y equals mx plus b and grows by the same amount every time, same amount every time, same amount every time. Every pattern that has a starting point and is always growing by the same steepness or the same slope will always form a straight line. Now, I did that just by going from the equation straight to the graph. You can do this with a table. If I plug in a 0, I get -8. If I plug in a 1, I get -5. If I plug in a 2, I get -2. If I plug in a 3, I get a +1. And then you just go through and graph these coordinates one at a time, and then you'll see that it will fall in a straight line. Now, most people find this to be a bit tedious and to take a long time. That's why it's important for us to be able to just look at the equation and get the graph without having to go through all the trouble of making the table. The rest of this lesson is all about the different ways this can look. It's about giving you examples and opportunities so that you can try this and make sure that you fully understand. So if you don't have a coordinate plane or a piece of grid paper with an x and y axis on it, you may want to print one of those before continuing with the video. Certainly if you're in my class, you already have this in a set of notes, and this should be pretty easy. But if you're just watching the video and you're not in my class, you will want to have some graph paper in order for you to try this as we go. Here's another one for you. Y equals 2x minus 5. Here's my graph or my coordinate plane. Again, I'm going to recommend, if you feel pretty comfortable, that you go ahead and try this on your own. I'm going to keep right on going so we don't have a lot of dead air time on the video. The first thing I do is I notice that this is in y equals mx plus b form. So this is in the slope-intercept form of a linear equation. Notice that my constant rate of change is a 2. And notice that I'm told that my starting point is a -5. If I put a 0 in for x, 2 times 0 minus 5 is -5. With these two pieces of information, I can graph every possible combination of x's and y's that work without having to go through the trouble of making a table. I would just start off at 0, -5, and I'm going to grow by 2 every time. That's up 2 over 1. There's my new dot. Up 2 over 1. Up 2 over 1, up 2 over 1, up 2 over 1, and I continue doing this. This begs the question, how many of these do I need to do? Well, I would say that if you are doing this for a grade, you're probably going to want to do several because you can do them pretty quickly, and it's very easy if you just graph 2 points and try and draw your straight line through it. It's very easy to be slightly off here, which may not seem like a big deal, but over time, it ends up causing your line to kind of stagger off to the side. Even if you use a ruler, even if these first 2 points are even slightly off, it is very difficult to get that exactly right. So I would suggest making sure that you extend your line out several points. In fact, instead of going up 3 over 1, sometimes I will even do down 3 and backwards 1 and get a couple points that way. Once I've got a really good set of points so I can see the graph, I draw my line. Everything on this line is a possible set of solutions. So when I look over here, this is what, 7, 9. If I were to plug in a 7, 2 times 7 minus 5 is 9. Then I come over here and do 8, 11, 2 times 11, or 2 times 8 is 16, minus 5 is 11, and I can continue on and on forever, and they will all fall in a straight line. I can also look here and I can see these values in between and figure out what's going on at 3.5 and 4.5 and 2 1/5 and those sorts of things. Not too bad, right? I'm going to erase all my ink. For some reason, I have a weird habit of drawing random ink dots places. Again, I'm going to recommend you pause the video, try this on your own. I'm going to keep on going. I look for my, my slope, which is 3/4, and I look for my starting point, 0, 1. You always start at your starting point. The slope 3/4 is sometimes difficult for students because it's hard to estimate up 3/4 of the way every time. It'd be something like right about here. That might even be a little bit too low. It's rather difficult to do, but if I go up 3/4 and then I go up 3/4 more, and up 3/4 more, and up 3/4 more, you'll notice that eventually I do end up at an intersection. And that intersection is the same intersection that I would have gotten if I had just gone up 3 and over 4 to begin with. Instead of trying to go up 3/4 every time, I just remember that this is going to be the same as my rise and my run. So I can go up 3 spaces and over 4 spaces. So that's what I'm going to do for the rest of these. Again, it's better for us when our dots are far apart because it keeps us from accidentally drawing our lines slightly askew. I also will do down and backwards a couple times so that I can draw a real nice, neat, straight line. Again, every point on this line is a possible set of x's and y's that will make this statement true. Here's another one. Pausing the video, trying it on your own, then restarting to watch. My rate of change is -4. My starting point is 0, 10. So I start off at 10. Now this says that I'm going down 4 every time. Down 4 over 1. Down 4 over 1. Down 4 over 1. And I continue that pattern on and on to draw my line. Some people get themselves confused and wonder, why wouldn't it be down 4 and backwards 1? And that's a great question. But if you think about your rise and your run, down 4 and backwards 1 is actually the same thing as a +4, not the same thing as a -4. That's how I know that this is going to go down and to the right, because down is negative, right is positive. -4 has to be down 4, forward 1. Or if you want to get really crazy, you could do plus or +4 and do backwards 1. That would be up 4, backwards 1. That would be a point back here someplace. Just keep in mind that when you've got a negative slope or a negative rate of change, as x gets bigger, you should be counting down. Here's one for you. I'll do this one a little faster because by now you should be getting much better at it. Your slope is -4/5. Your y-intercept is 0, -11. You can see my lines are just a little bit off. I'll fix that later. I start off at 11, down 4 over 5, down 4 over 5. That's all the room I have. Notice that I make sure my line goes from one end of my coordinate plane to the other. A lot of students get in the habit of drawing just like little lines here. Please don't do that, because a lot of times there will be follow-up questions that ask you what's going on down here. And if you only draw part of the line, it's very difficult to make the to draw a conclusion. So make sure that your line goes through whatever available space you have. How about this one? Start off at -1. Oops, is that a typo? Yes, it is. Start off at -1. Your slope or your rate of change is 8, so I go up 8 over 1. You could also go down 8 back 1, and there's your graph. Notice I cut mine off just a little bit. I really should have stretched that all the way to the end. Last one on this slide. This one's a little bit different. A lot of people do very, very well with the starting point being at 4, but a lot of people struggle with this constant rate of change because there's no number there. You can see that I told you your constant rate of change is a 1. That's because anytime you have a variable with nothing in front, it's always a 1, because 1 times anything doesn't change your solution. That's the identity property. So this is just going to be up 1 over 1 repeatedly, or you could do down 1, backward 1. That's fine as well. Once you've got a really long set of possibilities, you can draw your line, and there you go. This isn't too bad, right? If things are in slope-intercept form, it's really not hard for us at all to come up with the graph. There are two special situations that I want to make sure you are aware of. The first is a problem like this where you have y equals 7. Remember, the slope-intercept form of a linear equation has a rate of change of m and a starting point of b. But notice, this only has a 7. We only have the b. That's because there are no x's. Remember, 0 times anything is 0, so 0 times x is 0 plus 7. It makes more sense to us if we write it this way, because if we write it that way, we can see that our rate of change is 0, and our starting point is the coordinate 0, 7. So I start off at the point 0, 7, and when I go to do my slope, I have to realize that my rise is 0, but I'm not really given a run. The reason for that is it doesn't really matter what the denominator is. 0 divided by anything is going to come out as a 0. So I could make this a 9. 0 over 9 says rise 0, run 9. So I go up 0 over 9. I could make this denominator into a negative 8. 0 divided by negative 8 is 0, so I rise 0 and I run negative 8. Or I could pick basically any number I want here. Rise 0, run 7. Rise 0, run negative 2. It doesn't really matter, but what's important for us to realize is if I'm never rising, I'm going to end up with a horizontal line at 7. That's kind of cool, right? If I were to give you x equals positive 4, this one looks very similar in that it's not really in slope-intercept form, but this one has a lot of differences from this one over here. So I need to think about it slightly differently. When I go to graph this, the problem states that x is always a 4. That means that no matter what I put in for y, x will be a 4. Y doesn't matter. So I could put maybe a 0 in for y. Does that make it true? Well, is the x a 4? Yes. I could put a 4 in for y. 4, 4. Does this meet the condition? Is the x a 4? Sure. Or I could put in a negative 4 for y. Does that meet the condition? 4 equals 4? Sure. Y has absolutely nothing to do with the problem. It doesn't matter what value I pick. So every possible y will work, meaning that when I graph this, this vertical line always has an x value of 4. It says 4, 0, 4, 1, 4, 2, 4, 3, 4, 4, 4. It doesn't matter what y is because y has absolutely nothing to do with this problem at all. Now, the other way we think of this is when we talk about the slope, the rise and the run. Remember, slope is how much y changes compared to how much x changes. Well, since y doesn't matter, y could be basically any number. If I wanted to use the 9 and the 4, I could say 9 minus 4 is a 5. If I wanted to use the 4 and the 0, I could say 4 minus 0 is 4. This top number doesn't matter because when I do 4 minus 4, I'm going to get some number over 0. And that is a big no-no in math. We never, ever, 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 ever divide by 0 because we can't take something and divide it into no pieces. That would take divine powers. So, since it's not allowed or not permissible or not able to occur in math, we would say that this has no slope. It's important to remember two things, and people do often mix this up, so I would put a big star next to this. This is a huge, huge idea that will come up over and over again. You need to be careful. Anytime you say y is a number, it's always going to be a horizontal line that passes through that number. It's going to have a slope of 0. I'm going to write that in here. The slope is 0. But if you have x equals a number, that's what we saw over here. You're always going to end up with a vertical line that passes through that number. Since x equals 4, I get a vertical line at 4. This is going to have an undefined slope or no slope because we can't have a 0 as our run. We can't have a 0 as our run. This division cannot occur. Make sure you spend some time getting these straight in your head. People often mistake them. I will tell you why they mistake them, because when you see y equals 7, we've trained and studied so hard that the y-axis is a vertical line that we think y equals 7 must also be a vertical line. That is the exact opposite of the truth. Notice that y is our vertical axis, but y equals 7 is always a horizontal line. Same thing happens over here. We think x, we think, oh, the x axis is horizontal, therefore this must be horizontal. That is not the case. The x-axis is horizontal, but every x equals equation is a vertical line. Very difficult to keep those straight. Lots of practice, lots of repetition to make sure that we don't forget that. That's all we have for you here today. Hopefully this has been useful to you. Again, when things are in slope-intercept form, they are very, very easy to graph. It allows us to skip the table, saves us an awful lot of work. A lot of times we like to change equations that are not in slope-intercept form into slope-intercept form specifically for this reason, but that's a lesson for another day. If you got something useful out of this lesson, make sure you give us a thumbs up. Make sure you ring that bell to turn on your notifications because we're going to have lots of cool stuff coming out at Nunley Math over the coming weeks. As always, I do appreciate you taking your time to come and join us here today. I do wish you all the very, very best. Take care of yourselves. Bye-bye.